the talk is essentially the talk is about some very basic equations and inequalities which underpin stability and optimal control, and the underlying idea of this talk, actually, or my work over the last few years, is to provide what I would term as a systematically fundamental alternatives to the linear quadratic mean in controls and dynamics. So most of the students, when they enter into control, they actually, first things they learn linear quadratic control, and they learn the Lyapunov equations, which are quadratic Lyapunov equations. And typically this has a lot to do with the energy. So therefore it appears quite natural in the systems. But ultimately, it's not only about the energy. Often, especially in the modern applications, we may have to consider different criteria when actually it's not necessarily true that actually energy is the dominance. So therefore, we might like to look at the questions which don't necessarily involve quadratic functions. And effectively, what I've been looking to do over the last few years, I was trying to kind of understand and the link in an appropriate way concepts of Hermann Minkowski, who has made tremendous contributions and actually established fundamental results in convex geometry, and of course, two well-known scientists in our field, which is Alexander Lyapunov, father of modern stability theory, and Richard Bellman, father of the dynamic programming. Now, the outline of the talk is relatively direct, so it has a bit of material, but I'll try to actually go very quickly over certain parts. So there are three parts which are actually providing the basis and introduce some concepts that actually we can understand what you're talking about. So in particular, I would have to give you a few definitions from the Minkowski algebra of convex bodies. So, and then I'll have to actually recall the basic or the fundamental Lyapunov equality and the equation, inequality and equation. And then actually, this is the new part, which is Minkowski-Lyapunov inequality and equation. And I'll do the same for the quadratic Bellman inequality and equation, and then follow it up with the Minkowski-Bellman inequality and equation. So in terms of the Minkowski algebra of convex bodies, there are a few very basic functions that actually will appear throughout this talk, and I want to define them, and I want to discuss some of their fundamental and key properties. So one of the dominant functions in this talk, and in general, actually, in control theory, and you'll see the reasons why, is Minkowski function. Now, Minkowski function is typically defined on through a subset, convex compact subset of Rn that contains the origin as an interior point. An example of such a set is this set, which is essentially composes the union of the L2, L1, and L infinity norms in certain cons of the underlying space. And the function on the right is a Minkowski function. Now, this function is defined simply as a minimum over eta, where x belongs to eta s, where s is the given set and eta is non-negative. So effectively, you take a point, you start from 0, you have an array, and you expand the set or contract the set until the point is in the boundary of the set. And then this function has some very nice properties. It's essentially continuous and sublinear function. It's 0 only at the 0, and actually, essentially it's positive away from the origin, and it's a finite value. Now, essentially, because this function is sublinear, that means it's a positively homogeneous of the first degree and subadditive. That means you can restrict the attention to the unit sphere or unit ball, and that's therefore you can actually get complete representation of this function on a unit sphere. Now, the reason why this function should be familiar to all of us is essentially very fundamental fact that any vector norm on the Rn is generated by the Minkowski function of a zero-symmetric property set S in Rn. Now, a zero-symmetric set, it means that set is equal to its reflection minus S around the origin. And the closed unit norm ball is set S itself. And some examples are L1, L infinity, and L2 norms, where the typical norm, the balls are essentially the diamond, the ball, the circle, and the square. Okay, so this is some very well, it's a well-known function. You have encountered even if you didn't actually, this means, I mean, now, as I said, I'm trying to merge an interesting topic for a mathematical and engineering audience. So this refers to the students when I talk. So those of you who are much more versed with mathematics, you should accept my apologies in advance if I'm making things too simple or too slow. The other function, which is equally important, is the support function. Now, the support function is also interesting in a sense that actually this function is given by a supremum X transpose S in S, and is defined of a non-empty closed convex set in Rn. Now, if you look at the directions on the unit sphere, you take any direction and you find the maximum and you obtain the supporting hyperplane to the set. And you can do this for a number. Now, this for a number of points on the unit sphere. And this function is interesting in the sense that actually it provides an interesting one-to-one correspondence between non-empty convex sets in Rn and the support functions. In particular, if S is a non-empty convex set in Rn, its support function is sublinear, and vice versa. If F is a sublinear function, there exists a there exists a unique non-empty convex sets in Rn. Effectively, what this tells you, it tells you in mathematical terms that support function provides an isomorphic embedding of the space of non-empty convex sets in Rn into a convex cone of continuous functions on the unit sphere. Okay, so that's a kind of mathematical terminology, but this function is interesting for us because essentially it allows us to quantify set inclusion. So when we look at non-empty closed convex sets S1 and S2, to say that one set is included in the other one is equivalent to say that the support function is less or equal. Now, what I have overlooked to say is that essentially both Minkowski function and support functions are typically functions of two arguments, but typically the set or the first argument of two arguments. So the first argument is fixed. This set generates the function, and then you can evaluate function at any point in the underlying space. The other thing that actually you want to look at when you look at the support function is that actually if you want to compute support function of a Minkowski sum, that's a sum of support functions. Now, Minkowski set addition is nothing else than straightforward generalization of ordinary addition to the space of sets. That means essentially you take sum of all points from the sets as defined here. And the final thing that actually matters is if you look at the support function of a linear transformation of a set, this is equivalent to the support function of a set over appropriate linear transformation of the direction. Now, these three properties are key properties which we'll use in the establishing Minkowski-Lyapunov inequality in equations. But I would like to reiterate something from the computational point which matters. Now, what it matters, typically, when you start using notions like Minkowski addition and transformations of the sets, to perform explicitly these computations, this might be very complicated. But what these equalities in terms of the support function tells you, they tell you that actually you don't need to do explicit computation of Minkowski addition to figure out support function. You can use the sum of the support functions. And this is very important and a subtle point for computational reasons. The same applies for the linear transformation. Now, an interesting thing that links support function and the Minkowski function is the polarity. The polar set of a set S is an interesting object. It's defined through set of all points such that y transpose x less or equal than 1, where y ranges in a set S. And now to understand this, most of the students encounter duality of the vector norms, L1, L infinity, L2 to L2, L infinity to L1, and this shape has this polar set. Now, the key point that we want to understand here, and all these properties that I've given you are actually results, and some of them are theorems that you can find in the books by Schneider, Rockefeller, and Wetz, but I have extracted the facts which we'll use in the developments. So there are two facts we want to take a notice of. The first one is if S is a proper C set, then its polar set is also proper C set. And then actually, if you take a bipolar, you obtain the original set. So if you apply polarity on a polar set, you get the set which you start from. This, of course, under assumption that you work with the proper C set in Rn. Now, the other thing that matters is that actually Minkowski function of a proper C set is equal to the support function of its polar set S star. Okay, so this is the link that is crucial between Minkowski and the support function. So this property I would like you to take a notice of, G of Sx equals H of S polar X, and I want you to take a notice of these three properties. If you look at the sum and support function over Minkowski sum, that's a sum of support functions. If you look at the linear transformation, that's a support over suitably linearly transformed direction. And if we have this inequality between support functions, we have a set inclusion. Okay, so those few properties will be crucial for the further developments. And this brings me to kind of, and I think actually this is something that I would recommend that most of young students to look at the book, excellent book by Professor Gajic, who is with us in audience. He has written an excellent book on the Lyapunov equation. And if you look at the very simple setting, if you look at the linear dynamics in the Rn, which are generated by matrix A, and if you look at the quadratic decrease function x transpose qx, where q is a symmetric and positive definite matrix, then actually Lyapunov inequality simply is a functional inequality, which says for any point x, what you really want when you measure function at the next point in time, which is ax, and you add this decrease, you're not increasing the function. Now, this is simplest to think in terms of the energy, that essentially what it tells you, the energy kind of dissipates in the direction of the evolution of the system. Now, in the quadratic case, you have a sum of two quadratics, and you are comparing it to another quadratic. What you obtain linear matrix inequality. And this is a well-known and fundamental object in the theory, stability theory for linear dynamics. And the basic fact here is, if you take any Q, which is positive, definite, and symmetric, and you take any matrix A, you can find positive, definite, and symmetric P solving the linear matrix inequality, that is solving the quadratic Lyapunov inequality, if and only if matrix A is strictly stable. So this links the stability of the matrix, or the stability of this linear dynamics, and the existence of a suitable quadratic function in an if and only if manner, and that's what's important. Okay. Now, what happens with the equation? Now, actually, you convert this previous linear, actually functional inequality into functional equation, and you wonder whether you can actually solve the equation v of ax plus L of x equals v of x. And when you substitute your postulated functions, you obtain linear matrix inequalities. And it turns out, actually, you can again solve this under the same postulates, and the solution is unique and it easily characterizes this sum. Okay, so these are the two fundamental facts which have underpinned a lot of developments and a lot of theory, and they have been. Now, you'll notice that in most of these talks, when I talk about existing results, I'm avoiding a lot of so to speak, decompositions of the underlying spaces into subspaces, and because I'm taking regular case where actually Q is positive definite, and then actually I'm not considering possibilities that you might be stable in certain directions and not necessarily stable in the other directions, and then you have to involve different assumptions. But for simplicity, I'm looking at the most regular cases, understanding that underlying algebraic decompositions can be easily added to the underlying theory. Now, the point is, as I said, there is a tremendous amount of work done, and you can find this in the literature, and I would strongly advise young students to examine the book by Professor Gajic, which is a very, very nice book to look at. And this brings me to the first set of contributions I would like to discuss with you, and these are the concerned with the Minkowski-Lyapunov inequality and equation. So there is a number of papers that has been published, and most of them have been published in Automatica. It took a bit of time to refine the results and to bring them to the form which is the most acceptable, I would say, from my point of view. But if you wish, you can contact me. I can send you these publications, or you can just find them in Automatica. So the question is the same. Okay, we're looking at the linear dynamics, but what we're going to do now, we're going to say that the decrease function is a Minkowski function. Okay, and we are going to be given a proper set Q, and we're going to ask, can we solve the Lyapunov inequality in this case? And Lyapunov inequality with a decrease. Okay, so that means actually, can we actually, if we postulate that we are looking at the Minkowski-Lyapunov function, for obvious reason, because it's going to satisfy Lyapunov inequality and it's going to be Minkowski function, so that's why I call it Minkowski-Lyapunov function. Can we actually, is this a meaningful equation? Can it be solved? Okay. Now, the other thing is, of course, then you ask, if you answer yes to the previous question, actually, what happens if you actually convert inequality to equation? In other words, is the underlying space closed under this operation, so limit-taking operation, so to speak. Now, the question here is that actually, when I started looking at this problem, what actually surprised me is you try to find results in the literature, and you can't. Actually, I couldn't find any results to provide answers to this question. So luckily enough, I realized a link which allowed me to provide affirmative answers to those two questions. So the first thing that actually we're going to do, we're going to see what happens happens when a Minkowski-Lyapunov function satisfies Minkowski-Lyapunov inequality? What are the implications of that? So if we start from the Minkowski-Lyapunov inequality, and if we use the previously mentioned identities, so in particular, the first thing we're going to do, we're going to use the equality between Minkowski function and the support function of the polar sets. So that means we take polar sets and we take support functions. So we convert this equation in terms of Minkowski inequality in terms of the Minkowski functions to an inequality in terms of the support functions. The second thing, we're going to apply this linear transformation thing with the support function, and then we're going to apply the sum of the support functions. Okay, so this A goes to the A transpose, and then when we sum up A transpose P star plus Q star, they sum up in terms of the Minkowski. Now we are comparing two support functions, which actually gives us an equivalent set inclusion. So starting from Minkowski-Lyapunov inequality, we obtain an equivalent set inclusion. And of course, once we have this set inclusion, because you know that P is a proper C set, so P star would be a proper C set itself, and the left-hand side would be a proper C set, we can apply polarity and obtain the polar form of this set inclusion, which actually reverses the inclusion. And this, what we have derived in those few lines, actually gives us a fundamental property of the Minkowski-Lyapunov functions. So we can state the first theorem, which says the following: take any proper C set Q in Rn and take any matrix A. Minkowski function of a proper C set P in Rn verifies the Minkowski-Lyapunov inequality for the linear dynamics Ax with the Minkowski decrease function x to Qx, if and only if polar set P star of P verifies the set inclusion A transpose P star plus Q star subset P star, or equivalently, if and only if the set P verifies the second set inclusion. Okay, so this is something which gives you a complete characterization of all Minkowski-Lyapunov functions associated with the considered Minkowski-Lyapunov inequality. Now, the second thing is, you start looking at this set inclusion, and then you start wondering actually what this set inclusion is. What you really see, you see linear transformation of a given set, in addition of another set, and then being a subset of the set you start with. And you recognize that this property is a property of robust positive invariance of suitably defined linear dynamics. And this can be, again, quantified and can be put in mathematical terms. So if you start with the linear dynamics, okay, what we're going to do, we're going to create what I call polar linear dynamics, which means we're going to take a transpose of A, and now what is cost? It's going to go as a perturbation to this system. We're going to add it as a disturbance W, and W is going to be a polar of the set Q. Okay. Now, if you look at these other dynamics, which are essentially now polar uncertain dynamics, and if we recall the notion of robust positive invariance, what we're going to say, a set Z is robust positively invariant for these dynamics with respect to this disturbance set, if and only if A transpose Z plus W is subset of equal Z. Now, if you keep in mind this inclusion, and this inclusion, you recognize it is the same object. It is the same form. So that means that essentially the stability of this normal dynamics actually gets linked to the robust positive invariance of these polar dynamics that we have introduced. We will quantify that. Now, the second thing I want you to keep in mind is, when do we say that the set is the minimal robust positive invariance set? And minimality is considered with respect to the set inclusion, and it's considered over non-empty closed sets for the reasons, if you don't have closed sets, you cannot differentiate, and you might have certain issues, but because the set W is a property set, it's in fact enough to consider the compact sets. The minimal robust positive invariant set will be compact when it exists, when it's actually meaningful, when A is strictly stable. So the minimal robust positive invariant set is positively invariant set, which is contained in any other closed robust positively invariant set. Okay, so those are two things. Now, as I already said, Minkowski-Lyapunov equation is equivalent to this set inclusion. So in terms of the robust positive invariance, we can recast our fundamental property by a following statement. If you take any proper C set Q and any matrix, there exists a proper C set P whose Minkowski function verifies the Minkowski-Lyapunov inequality with the Minkowski decrease function. Oops, sorry, I jumped one slide too. Minkowski function verifies Minkowski-Lyapunov inequality for the system AX. X plus equals AX and Minkowski decrease function X to QX, if and only if polar set P of P is a robust positively invariant set for this polar dynamics, uncertain linear dynamics, okay? And then because these are proper C sets, and because Q is a proper C set, that means essentially H transpose P star is contracted. So that means you can satisfy this set inclusion if and only if A is strictly stable. So existence of Minkowski-Lyapunov functions with equivalently robust positive invariant set is completely characterized with strict stability of A. So you can make the following statement. There exists a proper C set P whose Minkowski function G of P verifies the Minkowski-Lyapunov inequality with a decrease Qx, equivalently whose polar set is robust positively invariant for the polar dynamics, if and only if A is strictly stable. So now this also tells you that actually considering stability questions for the linear dynamics is non-conservative over the space of Minkowski functions. You don't lose anything because if the system is strictly stable, you can find the Minkowski-Lyapunov function which is going to verify that property. All right, so that solves inequality. You have, I should mention that more precise proofs are given in my papers. I'm just giving some ideas. And now we start asking the question of equation. Can we solve the equation? Okay, so since you're attending the talk and since I'm giving the talk, the answer is affirmative. And actually what really happens, we follow the same sequence of the steps. Now, instead of inequality, we have equation. And what we obtain equality of two support functions. But equality of two support function converts to the set equation. So essentially, G of P comma AX plus G of QX equal G of P of X is equivalent to A transpose P star plus Q star equal P star. So if you can find the Minkowski-Lyapunov function which verifies Minkowski-Lyapunov equation, that means its generator set, when you take a polar of it, has to solve this fixed point set equation. And of course, you can take a polar on this side. So now we can restate the previous results in terms of inequality, but now in terms of the equality or equation. And the restatements follow. So Minkowski-Lyapunov equation, its equivalent set equation, fixed point set equation in set P star, and the polar form of this equation. So if you take any proper C set Q in any matrix A, Minkowski function x to G of P of X of proper C set P verifies the Minkowski-Lyapunov equation for the linear dynamics with Minkowski decrease function x to G QX, if and only if the polar set P solves the fixed point set equation. Okay, or equivalently, if and only if the set P solves the polar form of this equation. Okay, so this is the characterization or the fundamental property of this particular and special Minkowski-Lyapunov function. And of course, now this fixed point set equation was something that motivated my work because this fixed point set equation was also advertised very within the context of set invariance in a joint work with Professor Zvi Einstein, which I'm very proud of. And I'm not so sure if Zvi has joined us. He was planning to join this talk. So we have characterized the minimality of invariant sets in terms of suitable fixed point set equations. And this is a particular application of that theory to the case of linear dynamics. Now, that essentially means that generator of the solution to the Minkowski-Lyapunov equation when its polar is taken is actually the minimal robust positively invariant set of the suitably defined polar dynamics. Now, this is something that actually has motivated my work because it has revealed in many ways really fundamental polarity or duality relationship between two fields and two objects. Okay, and then of course when you can solve this, the condition is still the same if and only if A is strictly stable, namely when A is strictly stable, A transpose is strictly stable. So you get certain contractive map in the polar space, and you can solve this fixed point set equation properly. In fact, you can write down the explicit expression of the solution. And as I said, that's the minimal robust positive invariant set. Now, when one sums up the ramifications of these results, there are two key aspects that I would like to underline. The first one is theoretical ramification, and the second one is computational ramification. Both of them are important. In terms of the theoretical ramification, what the results say the stability analysis via Minkowski-Lyapunov functions of linear dynamics with decreased function Qx is conceptually identical modulo polarity operations to the robust positive invariance analysis over the space of proper C sets for the polar dynamics. So that means looking at stability questions or looking at the robust positive invariant questions, if you use duality, you can link them in one-to-one fashion. Okay. The second thing also is very important. It's computational because what it tells you, computing Minkowski-Lyapunov functions or computing robust positive invariant proper C sets, it is the same thing, again, modulo duality. So that means either you can compute both or you can't compute any. So if I can compute Minkowski-Lyapunov function, I take a polar set and I'm getting robust positive invariant set for the polar dynamics and vice versa. So it's not possible to make assertions that we can compute Lyapunov functions and we cannot compute the robust positive invariant set, because obviously just doing duality gives you the object you want. Okay. Now that closes the first part of the talk, and I'm hoping I'm doing okay with the time. This was an easier part, and as I said, this has resulted in a sequence of the papers. Most of them actually are listed. There is some other work that actually is ongoing on the computational aspects. But as I said, the key points to take here is that actually are these two main ramifications, theoretical and computational ramification. So there is essentially, mathematically, loosely speaking, and speaking properly in terms of engineering aspects, there is one-to-one correspondence between the theory and computations of Minkowski-Lyapunov functions and robust positively invariant sets. Okay, so that was the key point here. And now if you go to the quadratic Bellman inequality and equation, we're going to look at the control case. We're going to look at the linear control system in a discrete time. We're going to have the quadratic stage cost function, and we have suitably defined matrices, and we're going to actually look at the quadratic Bellman function. Now, what I use the term quadratic Bellman function is what is known as a cost to go function, or the value function within the language of Bellman. Now, what I call the Bellman functional dynamics, it's what's known as a dynamic programming equation. There are reasons why I want to use Bellman functional dynamics, because I want to see this as a functional dynamics, and then I want to look how I convert this to the set dynamics in the case of Minkowski. And then actually there are two objects. There is a value function and optimizer function. Now, value function is a minimum of this objective function, which is a stage cost and which is cost to go evaluated at the next state. Okay. Now here I didn't put the brackets, but this we can fix by assuming that actually addition of the function comes before the minimization. Okay. So I want you to understand that in the talk. Okay, just the rule. And the reasons why I didn't put the brackets is I think it's much simpler if you understand that we do first addition and then minimization. And also, if I put the brackets, I couldn't fit this nicely in the slides. It goes over the slides, so it breaks, okay? So you have to sacrifice something for aesthetics. And then actually the optimizer function is argmin. And now what I call quadratic Bellman inequality is essentially if the function v of x satisfies this inequality, functional inequality below. That means the value function, which I do after one step of the dynamic programming, if it's uniformly less or equal than v of x, then actually I'm obtaining also an increasing property or improvement, consistent improvement of this iteration. And this function has some special properties, and also in terms of stability, it gives you controlled Lyapunov property, okay? Right. So that's the inequality, and the same thing is for the equation. So now for the equation, essentially, I'm just wondering where. Now, what you're going to recognize when you start asking the question of quadratic Bellman equation, what you're really looking at, you're looking at the fixed point equation of the Bellman functional. You're looking at the fixed point of Bellman functional dynamics in my language, or you're looking at the fixed point of the dynamic programming. So you're looking at the function which solves the fixed point, which then gives you infinite horizon solution in regular case. Okay, so now I'll go through some basic facts for the linear quadratic case through in a sequence of slides. I will not be going in too much details, and I'll look again at the most regular case, which means I'll assume often that the things are positive definite. I'll assume the cost is positive definite to avoid detectability or observability condition on Q half and A, just to simplify, because this is not the topic of my talk. This is something that people can look up, but I want to make a kind of comparison of the results. So typically, as I said, this Q is a symmetric and positive definite. This is typically positive semi-definite in the literature, but then you have to have a condition on Q half and A to be observable. I have removed that again for the reasons it's an unnecessary algebraic distraction. And then R is positive definite, symmetric, P is positive definite. And then actually, if you look at this Bellman functional dynamics, if you look at this minimization problem, the solution is quadratic. And essentially, these Bellman functional dynamics are equivalent to the Riccati matrix dynamics. Okay, so to solve the Bellman equation over the space of the quadratics, what you actually end up with, the Riccati matrix dynamics. The way to do that is actually you obtain the objective function is a quadratic function. It's a strictly convex under my assumptions and differentiable clearly. Because it's differentiable, you set the gradient to 0, you obtain the linear optimizer, you plug it back, the value function is quadratic, and this is the equation you propagate. So we can use this as a matrix dynamics. So we have a dynamics of P, which actually characterizes the solution of the Bellman equations, and we have well, strictly speaking, it's not dynamics of K plus. You can see this as an output of a dynamical system, but essentially you accompany the gains or optimizer functions. Now, interesting feature here is you preserve strict convexity, you preserve quadratic structure, and the optimizer is linear. If you iterate this, you obtain the finite horizon linear quadratic regulator. This is well-known fact. All what you do, you start from a quadratic, you iterate number of times, you reverse the time. You have obtained the sequence of P's and sequence of K's, and that gives you time varying profile of optimal control. And then if we want to solve the quadratic Bellman inequality, what we're gonna, because we have an expression, closed loop expression for V plus and V of X, we obtain a matrix inequality. So this is the form of the inequality, and we can call this quadratic Bellman inequality, okay? Now, because I have assumed completely regular case, we can solve this if and only if AB is strictly stabilizable. Strictly stabilizable AB means that essentially if you do any decompositions, algebraic decompositions, you end up with a strictly controllable part and the strictly stable part. Again, this is to avoid unnecessary algebraic decompositions. And you can actually do this in more general by looking at the mixed cost when you have a positive definite cross terms. C transpose strictly positive, okay? Now, that tells you for inequality, if you look at the equation, you again obtain the fixed point of the Riccati equation, and this is nothing else than the infinite horizon linear regulator. And it is well known that actually solution is quadratic. It solves this sometime in engineering, it's called steady state Riccati equation, and optimizer is linear. So you have a closed loop form for the solution. Under assumptions I stated, you can solve it if and only if A is strictly stabilizable, in which case solution is unique. Now, this is important. If you drop assumption on Q to be just positive semi-definite, then you need to invoke the assumption on Q half A to be observable, as otherwise you may have multiple solutions, okay? Without this kind of observability, you might not be able to see certain directions, and the solution therefore might be non-unique. All right, so that sums it up. And now, this is what actually initiated all this work in a way. In 2018, I spent some time in Montenegro. I had the time to think about some things and was done the handbook and was preparing material for another book I'm trying to work on. And I kind of wrote up something which I called Minkowski-Bellman equation. And it took me a number of months to write 17 pages for Automatica. It went for the review, very positive feedback, and it got rejected. Okay, so now I started evaluating what happened, how it happened, and okay, I realized what was the problem. I put way too much material in one paper. So then the thing was to actually break it down into bits and pieces. And what I realized actually by developing this theory of Minkowski-Bellman equation, I have actually developed the theory for the control Minkowski-Lyapunov equation and also Minkowski-Bellman inequality and so on and so forth. And then actually I took this as an encouragement to break it down into smaller parts and to bring it together back. So kind of throw the stones and then bring the stones together. So and this went better. Okay, it got published and it's been accepted and it's out it's available publicly. Okay, so the problem is the same. We look at the linear control system. Now, what we're gonna work with the Minkowski stage function, gauge of CXU. C is a proper C set in Rn, and I'm now doing the mixed one, and I want to wonder. Actually, I'm wondering whether there is a Minkowski-Bellman function. That is, can I solve this functional equation in the space of Minkowski functions? So if I take objective function to be Minkowski function, will the value function be Minkowski function? And what will be its optimizer? That's essentially the problem you need to address. Now, if I can do that, can I actually then solve this Minkowski-Bellman inequality, which will tell me that the value function is less or equal than the current function, okay? And then I can do the same with the equation. Of course, if I can't do inequality, then it's unlikely I can do equations, because equation will be in many sense a limiting process of the inequalities, okay? So the first thing that we need to do, we need to figure out is the space of Minkowski function closed under this composition and addition of the functions? Because if that's not the case, then we cannot do anything else. That's going to stop us. The first answer is yes. Okay, so if you look at this objective function, we are summing up two Minkowski functions. We have linear transformation here. So first we can go to the polarity, via polarity to the support functions. Then we can do linear transformation here, which gives you these objects. Now we are summing up two support functions. So that gives us sum of the sets. And then we can again use the polarity of the support function and Minkowski functions. And therefore we can express the objective function as a single Minkowski function. Now it's an interesting trick because we have used the duality twice. Because the duality is used twice to perform this algebraic manipulation, I felt uncomfortable to call this result lemma or proposition, so I named it a theorem. Okay, so here is the first fact we can state. If you take any property set P and any property set C and any matrix pair AB, and if you look at this objective function, then this is a Minkowski function of a set T plus, which is given by this expression. Okay. Now, this doesn't mean you need to compute this set, but it gives you the closed form characterization of the function. We'll talk about computations later, but for the time being, we are still in business because the objective function that we are dealing with is a Minkowski function, okay? Now, the second question is a bit more complicated because now we need to figure out when we perform minimization, parametric minimization, will we actually still stay in the space of Minkowski functions? And you can recall, you can actually use here at this point in time the results by Rockefeller and Betz from variational analysis to establish this. And this is what they've done originally. And you end up with a proof on about 2-3 pages. But then actually, if you, now I'll tell you what's the difficulty here. So the major difficulty when you start dealing with Minkowski function is that you lose differentiability, okay? So quadratic case is very nice. So you have differentiability and you can actually do standard x. Everybody can do gradients, you equate gradients to 0 and etc. Okay? But the point is when you lose differentiability, you need to start using generalized or subdifferential, and that's complicated object. So therefore you need to have some geometric ways to characterize the solution. And it turns out you can do that. And interestingly enough, you can characterize this minimum function in almost direct manner. And here is what we do. So we have this set T, and we are looking at minimization of this function with respect to u for each x. What I'm going to do, I'm going to define a projection of T plus onto Rn, and I'm going to call that set P plus. So P plus is projection to the Rn, okay? And now I shall establish that this minimum of g of T of xu is actually gauge of Px, P plus x, okay? To see that, first, if you take any x, and if you work Minkowski function, then you know that x is inside of g of P of x, P plus. By definition, there would be a point V such that xv is in g of P plus xt plus, okay, by convexity and property structure of this. That means that if I look at the minimum of g of T plus xu over u is going to be less or equal g of P of x. That's one side of inequality. Now, on the other side, this minimum is well defined because this is a continuous function, suitably level bounded. Properties I have already indicated. That means that essentially for all x, there is a v such that xv is inside of the minimum of g of T of plus of xu T plus, okay? So that means, because P plus is a projection, that x is a minimum of P plus, which means that g of P plus x is less or equal than minimum of u, g of T plus xu. Now, you have this inequality and you have this inequality, which gives you equality. So therefore, there is an equality, and now what it says that essentially the space of Minkowski functions is also closed under the parametric minimization. Okay, that's an interesting fact. Now, this shouldn't come as a surprise because if you look at the parametric minimization in Rockefeller's book, what he tells you you take the epigraph of the objective function, you project the epigraph onto the space of the parameter, and you take epigraph of value function, and that is a correspondence. That's how you solve the parametric optimization in most general case. Now, what I've done is much more direct because essentially I have utilized the structure of Minkowski functions and their properties, okay? So this now gives us the minimization, and we need to discuss what is the minimizer. How do we characterize the minimizer map? Well, we have now this equality. So what we're going to say, the set of points that actually is minimizing this function is any point which gives you this function to be less or equal than the value function. And when you reorganize this, you obtain this semi-explicit characterization. So the optimizer map is at any x given as a set of all u's such that this is inside of G of P plus XT. Now, this will give you characterization in geometry. What it means, if I pick a point X, which I call Z here, because this is vertical to the space I'm projecting, any point in this set is optimized. Okay, so that's a pointwise optimization. If I've done this parametrically, I would get these conic maps. Okay, and I'll characterize these maps because I have the closed loop form, so it's very easy to describe their topological properties now. Okay, so, but let's summarize what we've done. If you take any proper C set P, any proper set C, C gives you the stage cost, P gives you the cost to go, or the in terms of the optimal control or model predictive control, it gives you terminal cost. So if you look at one step, we already know that the objective function is Minkowski function, but we know that the value function is also Minkowski function. And the optimizer map is given by this expression here. It's a very nice expression because it links the Minkowski function, which is value function, and the generator of the objective function. And you have these closed loop form expressions for the generator sets of the Minkowski functions which are involved. Okay, so now, it's tempting to assert that this optimizer function is continuous because everything is nice, convex, and so on, but this is not true. This would be a false statement. And actually, when I was working on this, as I said, I'm really privileged and glad that I had the opportunity to establish friendship with Zvi Einstein. And if Zvi is present, I apologize to him for many questions I have from time to time, but this is one of the questions I had with him, and we discussed it, and he came up with an excellent example, which then I converted to the dynamics. An example geometry is here. This shows you that actually you may end up with outer semi-continuous optimizer maps. So the dynamics are trivials, A and B are 0. The P is just the Euclidean norm ball, and set C is given as here, essentially Euclidean norm ball added with this segment, and then you take a convex half. So then the Euclidean norm ball gives you the fixed point solution. And essentially what you see at this particular point, your solution is multi-valued where everywhere else is just this black, okay? So this is where you lose continuity, but you still preserve outer semi-continuity, which is very important because essentially it tells you that the graph of the optimizer function is closed set, okay? Now, let's sum up this. Because Minkowski function is positively homogeneous, optimizer map is positively homogeneous because this is a proper C set. Because Minkowski function is finite valued and this is a proper C set, this is a compact and convex valued map. Because Minkowski function is again finite valued, this is locally bounded. But it's not enough that it's just a finite value, it's important that it's sublinear because it's sublinear and positive in finite, you can actually establish that it's locally bounded. And finally, because this is a continuous function and this is a proper C set, this map is outer semi-continuous, its graph is closed. Now, what it means, since it's locally bounded and outer semi-continuous function, it means that actually this is a positively homogeneous of the first degree and continuous function when it's single valued. When it's single valued, it happens when actually you have this T plus to be continuously differentiable or to be strictly convex set. In that case, actually you get continuity, you get stronger properties, okay? Now, just to give you examples, what may happen, these are the trivial polytopic examples, one-dimensional, so you can actually see it's a fixed point solution. In this case, solution is linear. It's a single valued. P is -1, 1, C is infinity norm ball in 2 dimensions. Now, if you change a bit, so you increase the first direction for the C, then actually you get multi-valued solution. And now what happens with multi-valued solution, as one would expect, actually, when you have orthogonal, when you have a vertical kind of part of the set with respect to the projection, then you get multi-valued solution. So this is what happens here. It's a vertical hyperplane on the projecting subspace. So that's when you get the multi-valued solutions. But still, an interesting thing to observe, because this is a polyhedral case, is actually you see here that actually you have continuity even when it's a multi-valued solution is continuous. And in fact, in a polyhedral case, you can state that the solution is Lipschitz continuous with respect to the Hausdorff distance. I'll come to the refinement. And this is a consequence of the finite nature of polyhedral sets. Okay. Now, this is the key point when we start using it for control. We have a very nice characterization. Now we can say a bit more about it. So if you look at these dynamic programming equations or Bellman functional dynamics, what we can say, they're essentially equivalent to the Minkowski set dynamics. What we need to do, we can propagate the generator sets and we can write down explicitly solutions, okay? So that means In the quadratic case, you started with the quadratics. Quadratics were essentially generalized by matrices. So you had the matrix dynamics underpinning the Bellman equation. You start with the Minkowski functions. Minkowski functions are generated by sets, so you have dynamics of sets, and I call it Minkowski set dynamics. It's obtained through this polarity, addition, and polarity again, and projection. So you have a closed loop form. Now, I would like to say this is a kind of general form of Minkowski functions, so it's pretty good. You can refine these characterizations for Minkowski functions. Now, the second thing is, if we iterate this, what we're going to get something which is fair to call finite horizon linear Minkowski regulator, because now we use Minkowski function as a criteria for the regulation. Now, if you look at the Minkowski-Bellman inequality, what we're going to ask g of p plus x less or equal g of px. But because we have explicit form for a p star, and because comparison of Minkowski function reverses the inclusion, we obtain a closed loop form expression. And this was a new result also within this context. So essentially, Minkowski function x to gp of x of proper C set verifies the Minkowski-Bellman inequality if and only if generator P satisfies this inclusion. Okay, so this is an interesting result in its own right. Okay, now when can we solve this? Because C is a proper set, and A, if you take any B, there are some ramifications. If you can solve this Minkowski-Bellman inequality, particularly because C is a proper C set, that means essentially you can do control stabilization of the origin. So that means AB has to be strictly stabilizable. On the other hand, if AB is strictly stabilizable, I can take some K and find an arbitrary P, which is going to give me upper bound, and then I can find the P to solve Minkowski-Bellman inequality. So that essentially means I can solve Minkowski-Bellman inequality if and only if matrix pair AB is strictly stabilizable. Once again, I would like you to take a note of the fact that I have invoked the proper C structure of the set C to avoid any unnecessary algebraic decomposition into subspaces, which diverts the attention from the conceptual aspects of this work. Okay, so now equation, this is the most interesting. Well, it's a functional equation, which when we use explicit forms of this function converts into fixed point set equation of the Minkowski set dynamics. Okay, and we can say that Minkowski function verifies the Minkowski-Bellman equation if and only if its generator set verifies the set equation. Okay, now this is an analogy. If you remember in the quadratic Bellman equation, what you had, you verify the fixed point of the dynamic programming or Bellman functional dynamics if and only if there was a fixed point of the matrix dynamics, Riccati matrix dynamics. So there was a matrix equation. Now in this case, we have a set equation, and it's quite logical and it's quite natural because essentially we are dealing with the functions which are generated by sets instead of the matrices. Okay. Finally, what do we know about this? If we solve this, we are obtaining the infinite horizon solution. Okay, so this will give you infinite horizon linear Minkowski regulator. And again, if you can't solve this, you can solve it if and only if AB is strictly stabilizable, and in that case, P is unique. Now, the proof of this fact is a kind of highly non-trivial. It's very intuitive, but I had to use rather sophisticated theorem for engineering. It's called the Blaschke selection theorem, which says that from any sequence of the bounded convex sets, you can extract convergent subsequence. This is for finite dimensional spaces. And then actually that would give you existence of a fixed point. And then actually the uniqueness would be obtained from the asymptotic stability of underlying dynamics. But actually on a reflection, once you publish things and you avoid the referees and comments and criticism, you get more time to think. I think this can be now proved using more direct lattice theoretic arguments and using Tarski fixed points arguments. Okay. So to give you an example, now this is more for engineering. So I'm giving you a cost which actually has a quadratic nature in the second and the fourth quadrant. It has an infinity norm nature in the first quadrant and has a one norm nature in the third quadrant. So you mix all these norms in a kind of union fashion, and this is the Minkowski function. So you can see difficulties. This is where you lose differentiability at this point. This is when you have to do subgradients instead of gradients. And this is the expression, and you do iteration. First iterate, this is the generator, this is the value function, this is second iterate, this is the value function, this the value function of a unit sphere because it's positively homogeneous, so you can look at the solution over the unit, actually unit ball, the boundary, the contour of the function would be just the black contour would be just on the unit sphere. P3, V3, P4. Now, in this example, numerical convergence is very fast, so solution has converged in few steps. So this is the infinite horizon solution. You see the function is relatively nice. It's a Minkowski function. Optimizer in this case is unique, and it's very interesting. It's a kind of piecewise affine function. Okay. Now, Kale, how much time do we have? Because I think I might have run like, so I can very quickly, I can skip polytopic case and people can look at the slides and just conclude, or I can go through the polytopic case, whatever.
I will suggest that you wrap up. So we have a few minutes for some questions, Sasha.
Can I just go over 2 slides? Just final 2 slides.
Sure.
Okay. So for a polytopic case, you can say that the value function is finitely many pieces piecewise linear. The optimizer is polytopic valued. Its graph is finite union of polyhedral cones, and its ellipse is continuous with respect to the Hausdorff distance. But you cannot guarantee this for fixed point because the limit of polytopes may not be polytope. Okay. And I'll go into conclusions, and this is now I've given you the basis. The true power of these notions comes from actually looking at more complicated or robust problems. So in particular, you can extend this to the cases of switching systems or linear discrete inclusion. So you can develop the notions of robust Minkowski-Lyapunov functions and robust Minkowski-Lyapunov equation. You can actually move these notions to the control cases. So you can do control Minkowski-Lyapunov case, and you can do robust control Minkowski-Lyapunov case. And there is a work that actually I have in progress with Professor Jacimovic, who has also joined us from Montenegro. He's an academic of Montenegro Science of Academy. He's a par excellence mathematician, and we joined the forces to develop the things in terms of the robust linear Minkowski regulator. And now we are in the process of let's put it this way, fighting the referees. Okay, so now when you develop some basic theory, people think solutions are simple, but you know, if you remove one's results, how do you develop results? That's kind of quite questionable. So, and I'll close with 2 slides. I'm sorry, I kind of overdone it a bit. So the first one is message for Kalman, which I think is very interesting for young students. At the 17th IFAC plenary in 2018, when Kalman has asserted that the further significant advances in control will happen when element A becomes a standard in control. But this has been already observed in the control. The set valued methods are already overtaking. They have increased popularity. However, I do want to say there are people like my dear friend Zvi Einstein, people like even Ponchagin, and people like Kujansky, Krasovsky, Oban, Varaya, Elia Pollack, Rockefeller, who have developed set valued analysis and calculus, and this has been done since the 60s. So if we do control, we have to really keep in mind that people have provided tools for us, and we have to use them appropriately rather than trying to reinvent the hot water. Now, to sum it up, it's an increased popularity in a contemporary control theory in applications. This is a conceptually powerful and topologically flexible notion. This refers to set valued analysis and calculus, but it does offer non-trivial computational challenges. Okay, and what is rather peculiar to me, the results I developed and presented all this over the last few years, they are novel. Actually, that was the most shocking part to me. I could not find anything properly in the literature, but they are fundamental in my opinion. And I want to close by acknowledging rather constructive feedback on a number of cases by my dear friend Zvi Einstein, and also encouraging and stimulating discussions with Raphael Goebel, who is a student of Terry Rockefeller, also an excellent young mathematician. But as I said, even the example that I presented, which points out the lack of continuity, is the example that actually has came from the discussion. Actually, it's an example that Zvi Einstein has created. I just modified it for the purpose of my paper. Okay, so I'll try to answer any questions you might have, and I'm sorry if I kind of spend a bit more time than I was allowed. My apology. Mea culpa, Domini Dominus.